On June 23, 2026, a spacecraft that is not even pointed at Earth saw it first. The European Space Agency's solar orbiter was out beyond the edge of our view, looking at the part of the sun we never get to see, the far side, the hemisphere that's always turned away from us. And there, rotating slowly toward us at the pace the whole sun turns, was a sunspot group big enough that the people who watch the sun for a living stopped what they were doing and sent out a warning. Now think about that for a second. We track the sun with more instruments than almost anything else in the sky. Telescopes on the ground, satellites parked between us and the star, a whole government office in Boulder, Colorado, whose entire job is to forecast the weather 93 million miles away. And the thing that got their attention this week, they couldn't even see directly. They saw it coming around the corner. Its name is Boring, Active Region 4478, AR4478, a string of numbers a computer assigned to a patch of magnetic chaos on the surface of the sun. But here's what isn't boring. On June 23rd, the National Oceanic and Atmospheric Administration's Space Weather Prediction Center did something they almost never do for a single sunspot. They put out a special public bulletin, a heads up, aimed at you. They don't do that for ordinary spots. They do it when a region is large and complex and rotating into the line of fire. And as it came around the southeastern edge of the sun, before it had even fully turned to face us, it fired a flare, Class C 8.7, clocked at 23:18 Universal Time on the 23rd. And that number is almost certainly too low, because the flare went off while the region was still partly hidden behind the curve of the sun. We measured the part we could see, the rest was around the corner. So here's the question this whole video is going to answer. Why are the forecasters worried about a sunspot in a year when everyone keeps telling you the sun is calming down? Because that, right there, is the lie. And by the end of this, you're going to understand exactly what AR4478 is, what it can actually do to the ground under your feet, why the most dangerous space weather in living memory did not happen at the peak of the cycle, and why the thing NOAA is watching right now is going to swing around to point straight down the barrel at Earth over the next 9 days. You'll understand it better than the people screaming about it online, and you'll understand why the truth is more unsettling than any of the conspiracy versions. This is the Horizon Lab. We don't do panic here. We do the real data, on screen, with the receipts. If that's the channel you want watching the sky for you, take a second and subscribe, because this story is still unfolding and we're going to be on it. Let's get into it. Because there's a detail in that NOAA bulletin that should stop you cold. The region they flagged isn't even aimed at us yet. Right now, this week, AR4478 is rounding the eastern limb of the sun. The side, anything it throws off right now goes wide, mostly past us. But the sun rotates. About once every 27 days, every feature on it marches across the disk from one edge to the other, and the middle of that march, the spot directly facing Earth, is the kill zone. That's the position where a cloud of charged particles launched off the surface comes straight at the planet instead of flying off into empty space. And AR4478 reaches that position at the end of this month, between roughly June 27th and the first days of July. So we have a large, magnetically complex sunspot region. We have it already throwing flares while it's barely in view. We have a forecasting agency concerned enough to break its own routine and warn the public early. And we have the geometry slowly, mechanically, turning that region until it's aimed at the one planet in the way. The forecasters know all of this. They've seen this movie before. They've seen what happens when people decide the threat is over a year too early, look away, and get caught in the dark at 2 in the morning. I'm going to show you exactly when that happened. I'm going to show you the 90 seconds it took to put 6 million people into a freezing blackout. But first, you need to understand what's actually sitting up there on the sun right now. Because to know why the experts are nervous, you have to know what a sunspot really is, and it is not a spot. Let's talk about that bulletin, because it's the part most people skip right past. The Space Weather Prediction Center puts out forecasts constantly, 3-day outlooks, 27-day outlooks, alerts, watches, warnings, the whole machinery, running around the clock in Boulder. Most of it is routine, Most of it is numbers updating on a dashboard that maybe a few thousand space weather nerds refresh every morning. I'm one of them. Maybe, after this, you will be too. But on June 23rd, at 8 minutes past 3 in the afternoon Universal Time, they posted something different. A news item. Plain language. Headline: a large sunspot group is going to rotate into Earth view on the 24th. Not an automated alert triggered by a sensor crossing a threshold. A human being at a forecast desk decided the public should hear about this one early. Why does that matter? Because agencies like this are careful. They are conservative by design. They do not cry wolf, because their entire credibility, and the credibility of every real warning they'll ever issue, depends on not crying wolf. When they break routine to point at one specific region, before it's even facing us, they are telling you something with the volume turned down. They're telling you, keep your eye on this one. So what did they actually see? A region that, on the far side imaging from solar orbiter and on the magnetic maps, looked large and looked complex. And in this game, complex is the word that matters. Not big, complex. Here's the difference, and it's everything. A sunspot can be huge and still be quiet, if its magnetic field is simple. One pole, one polarity, tidy. That kind of region just sits there. But when a region has multiple poles tangled together, north and south magnetic polarity crammed into the same patch, twisting around each other, shearing, that's a region storing energy. That's a spring being wound tighter and tighter, and springs wound that tight eventually let go. The first sign that this one had a temper came almost immediately. As it cleared the edge, it threw a flare measured at C 8.7. Now, on the scale we use, C is the low rung. A, B, C, then M, then X, each letter 10 times stronger than the one before. A C-class flare on its own is nothing to lose sleep over. But remember the geometry. This flare went off while the region was still partially behind the limb of the sun. We only measured the X-rays that made it over the horizon. The true output was higher, maybe much higher, and we simply couldn't see the bottom of it. It's like hearing a sound from around a corner. What reaches you is muffled. The real noise, the source, is louder than what your ears report. And this is not happening in a vacuum. Just 2 days earlier, on June 21st, a different region on the Sun, AR4478, fired an M6.8 flare at 17 past 7 in the evening Universal Time. That one caused an R2 radio blackout, real impact, real degradation of high-frequency radio on the sunlit side of Earth. So the sun that everyone keeps describing as winding down for the year, fired a significant flare on the 21st, and then served up a brand new complex region on the 23rd. Does that sound like a star that's done? Look at what the forecasters actually wrote for the days ahead. In the 3-day forecast issued at midnight Universal Time on June 25th, NOAA gave a 50% chance of R1 to R2 radio blackouts on each of the next 3 days, and a 10% chance of an R3 or stronger event each day. And they named the reason. They wrote it down. The elevated risk was, in their words, due primarily to the flare potential of region 4478. They named it, they put a number on it, 50-50 for a blackout, every day, for 3 days running, because of this one region. Let me say that again, because it matters. The chance of a radio blackout caused by AR4478 was running at 1 in 2 per day. That's not a fringe forecaster on the internet. That's the United States government's official space weather office. So we have the warning, and we have the receipts behind the warning. What we don't have yet is the thing underneath all of it, the mechanism. Because to understand why a dark patch on the sun can reach across 93 million miles of empty space and knock out the power to a city, you have to understand what that dark patch actually is. And the answer is going to change how you look at the sun for the rest of your life. A sunspot looks dark. That's the first thing your eye gets wrong about it. It looks dark, so your brain files it as a hole, a gap, an absence, something cooler and quieter than the blazing surface around it. And the cooler part is true. A sunspot is around 3,000 degrees, while the surface around it runs closer to 5,500. Set side by side, the cooler patch looks black against the glare. but it only looks dark the way a candle flame looks dark if you hold it in front of the sun. It isn't dark, it's just standing next to something brighter. A sunspot is not a hole in the sun, it's a knot in the sun's magnetic field, punched right up through the surface. Here's what's happening underneath. The sun is not a solid ball, it's a churning sphere of plasma, electrically charged gas, and it doesn't rotate all in one piece the way Earth does. The equator spins faster than the poles, and buried inside, the sun's magnetic field gets caught in that uneven spin. The field lines, which start out running cleanly from pole to pole, get grabbed by the faster-moving equator and dragged, wound, stretched around the star like thread around a spindle, over and over, until they're twisted into tight, buried ropes of magnetism. And every so often, one of those ropes gets so buoyant and so tightly wound that it floats up and breaks through the surface. Where it punches through, it chokes off the normal flow of heat rising from below. That patch cools, that patch darkens. That's your sunspot. The dark spot you see is just the visible footprint of a magnetic rope the size of a planet, sticking up out of the sun. Now picture not one rope, but a tangle of them, crowded together, some coming up, some going back down, north poles and south poles jammed into the same neighborhood, all of them under strain. That's a complex region. That's AR4478. And all that twisted magnetic field is storing energy the exact way a wound spring or a bent steel bar stores energy. It wants to snap back to something simpler. It's just waiting for a trigger. When it snaps, we call it magnetic reconnection. The tangled field lines suddenly break and reconnect into a simpler shape, and in doing it, they dump a staggering amount of stored energy all at once. The biggest flares release the energy of billions of hydrogen bombs in a matter of minutes. That energy comes off as a flash across the whole spectrum: X-rays, ultraviolet, radio, light, a solar flare. And here's the first thing you have to keep straight, because almost everyone online gets it wrong. A flare is light. It's radiation. It travels at the speed of light, which means when you see a flare happen, it has already arrived. The X-rays from a flare hit the sunlit side of Earth's upper atmosphere 8 minutes after they leave the sun, because that's how long light takes to cross the gap. There is no warning for the flare itself. By the time the instruments register it, the radio blackout on the daylight side of the planet is already happening. That's what an R-scale blackout is. The flash of X-rays slams into the upper atmosphere, thickens it, and high-frequency radio signals that normally bounce off it get swallowed instead. Pilots on transoceanic routes lose contact. Mariners lose signal. It's already over, before anyone could have told you it started. But the flare is not the thing that takes down a power grid. The flare is the muzzle flash. The bullet is something else. Sometimes, along with the flash of a flare, the sun launches a piece of itself, a coronal mass ejection, a CME, a billion tons of magnetized plasma blown off the surface and hurled out into space. And unlike the flare, the CME is matter, not light, so it's slow. Relatively slow. It takes anywhere from about 15 hours to 3 days to cross the distance to Earth, depending on how hard it was thrown. That delay is the only warning we get. That's the entire window. When a CME launches off a region that's facing Earth, the satellites between us and the sun catch it, measure its speed and the direction of its magnetic field, and forecasters get somewhere between a few hours and a couple of days to say, "It's coming, and here's how bad." So now you understand the two weapons. The flare, which is light, which arrives the instant you see it, which blacks out radio. And the CME, which is matter, which takes a day or so to arrive, and which is the thing that reaches down through the atmosphere and pushes electric currents through the ground and through the wires we built across it. A complex region like AR4478 can produce both, and it's about to rotate into the position where, if it throws a CME, that CME comes straight at us. But you've been told not to worry. You've been told the sun is settling down. So let's talk about where that story came from. Because it's not wrong exactly. It's just dangerously incomplete. Here's the comforting version, the one you've probably absorbed without even noticing. The sun runs on a cycle. Roughly 11 years long, peak to peak. It swings from quiet to active and back again, and we count the swings. The one we're in now is solar cycle 25. the 25th since we started keeping formal track back in the 1700s. During the quiet years, the surface is nearly blank. Few spots, few flares. During the active years, the solar maximum, the surface breaks out in spots and the flares come fast. And in October of 2024, NASA and NOAA stood up together and announced that solar cycle 25 had reached its maximum. So the story writes itself, doesn't it? Maximum means peak. Peak means the top. And after the top, everything goes downhill. We're now something like 20 months past that announced maximum. The logic feels airtight. The worst is behind us. The sun is on the downslope. Time to relax. You can see why people believe it. It's intuitive. It even sounds scientific, because it's built on a real thing, the real solar cycle. The headlines reinforce it. Every few months, another article runs about the sun winding down, the aurora season ending, the show being over. And right now, in late June, there's an extra layer of false comfort stacked on top. And it's worth naming, because it fools people every single year. It's summer in the northern hemisphere. The nights are short. We just passed the solstice, the shortest nights of the year. And aurora, the one piece of space weather most people have ever actually cared about, needs dark skies to be seen. So even when the sun does kick off a storm right now, hardly anyone in the United States or Europe sees the lights, because there's barely any darkness to see them in. No green glow on the horizon means no viral photos. No viral photos means no headlines. No headlines means the public quietly concludes nothing is happening. But the absence of aurora in your sky is not the absence of activity on the sun. Those are two completely different things. One is about the angle of the Earth and the length of your night. The other is about billion-ton clouds of plasma and the magnetic state of a star. The sun does not check your local sunset time before it fires. So we've got a perfect storm of complacency, a real cycle that genuinely is past its announced peak, a summer that hides the only symptom most people would notice, and a steady drumbeat of well-meaning coverage telling everyone the dramatic part is finished. And almost all of it rests on one buried assumption, the assumption that maximum means most dangerous, that the peak of the sunspot count is also the peak of the threat. That assumption is wrong. Not slightly wrong, not a technicality, wrong in the specific way that has, more than once, caught the modern world flat-footed and put millions of people in the dark. Because the number that NASA and NOAA track to call the maximum is the sunspot number. How many spots? How often? And yes, that number does peak and then decline, but the biggest, most violent, most damaging individual events, the flares and the CMEs that actually reach across space and hurt us down here, do not reliably line up with that peak. They have a nasty habit of showing up afterward. On the downslope, during the very phase everyone has already decided is the safe one. There's even a name for the tendency. The declining phase of a solar cycle is known for producing some of the most intense space weather events of the whole cycle. The fireworks don't always come when the crowd is the biggest. Sometimes they come after half the crowd has gone home. I want to be careful and fair here, because being accurate is the whole point of this channel. The people writing those calming headlines are not lying to you. The cycle really has passed its maximum. Activity, on average, really will trend down over the next few years. If you're an average person planning an aurora trip, the easy viewing odds really are slipping away with every short summer night. But average is doing a lot of work in that sentence. Average trends down. Individual monsters do not care about the average. And it only takes one region, complex enough, aimed the right way, at the wrong moment, on a downslope when everyone stopped watching. So if the maximum isn't the most dangerous moment, when is? Let me bring in someone who would know. In October of 2024, when NASA and NOAA made the announcement that solar cycle 25 had hit its maximum, one of the scientists who co-chaired the prediction panel said something that did not make the cheerful headlines. Her name is Lisa Upton. She's a solar physicist at the Southwest Research Institute, and her job, literally, is forecasting the shape of the solar cycle. So when the rest of the coverage was running with, "The sun has peaked," here's what she actually warned. She said that even after the solar maximum has passed, high-impact space weather is still possible. And then she added the part that should make you sit up. She said the declining phase is notable for often having very strong solar events. Read that again. The person announcing the peak was, in the same breath, telling everyone that the dangerous part might still be ahead. Not behind, ahead. Why would that be? It sounds backwards. Fewer spots, but bigger storms. How does that work? Think of it less like a single mountain and more like a long ridgeline. The sunspot number, the headline count, climbs to a peak and then starts dropping. That part is real. But the regions that survive on the declining slope tend to be different in character. As the cycle ages and the sun's magnetic field reorganizes itself for the next cycle, the regions that do appear can be larger, more sheared, more magnetically complex. There are fewer of them, so the average goes down, and the headlines follow the average down. But complexity is what makes a region dangerous, not head count. One savagely complex region on a quiet slope can outgun a dozen tidy ones at the noisy peak. Fewer guns, bigger guns. And nobody's watching, because the count went down. That is the lie of the calm. Not a lie anyone told on purpose. A lie of omission, baked right into the way we summarize the sun. We reduced a violent, complicated star to a single rising and falling number, and then we let that number tell us when to be afraid. And the number is most reassuring at exactly the moment it's most misleading. Here's the uncomfortable shape of it. At solar maximum, the danger is high and everyone knows it. The headlines are loud, the aurora are everywhere, the forecasters are on television. Attention and threat are matched up. But on the declining phase, the threat stays meaningfully high while the attention collapses. The gap between how dangerous it actually is and how dangerous people think it is, that gap is widest on the downslope. And a danger you've stopped watching for is worth more to that danger than one you're braced against. Now layer on everything we already said. It's summer. The nights are short. The aurora, the one symptom the public tracks, is hidden by the season. Add the genuine, accurate, well-reported fact that the cycle has passed its peak. Stack those on top of the buried assumption that peak equals worst, and you've built a population that is, right now, in the early summer of 2026, about as unbraced for a major solar storm as it ever gets. And into that gap rotates AR4478. I want to keep my promise to be fair, because the difference between this channel and the panic merchants is that we don't oversell. I am not telling you that AR4478 is going to launch a civilization-ending storm next week. I have no idea, and neither does anyone else, because that specific prediction is not something the science can make. What I'm telling you is something narrower and honestly scarier because it's true. The conditions that have produced the worst space weather disasters of the modern era are the conditions we are in right now. A complex region, on the declining phase, rotating toward Earth, at a moment when public attention is at its lowest. That's not a forecast of doom, that's a description of the setup, and the setup is real. So how do I know the declining phase actually bites? Because it already has. Twice, within timeframes you can verify, the sun has fired its biggest shots of an entire cycle well after the peak everyone fixated on. Not legends from the 1800s. Modern events, satellites overhead, instruments running, dates on the record. The first one came in the autumn of 2003, 2 years after the maximum. The experts had already filed that cycle's danger under past tense. And then, over about 2 weeks, the sun let loose one of the most intense barrages of the entire space age. They named it after the season it ruined, the Halloween storms. Let me take you there. Solar Cycle 23 peaked around the year 2001. By the autumn of 2003, by every comfortable assumption, the worst should have been behind us. The count was down, the cycle was aging, 2 years past the top. Then, in late October, the sun woke up in a way that the people watching it have never quite forgotten. Over roughly 2 weeks, spanning the end of October and the start of November, a cluster of enormous, furious, active regions rotated across the face of the sun and fired off one of the most intense series of flares and coronal mass ejections of the entire modern record. 17 major flares in those weeks, multiple X-class monsters, the top rung of the scale, and one of them ran straight off the end of the chart. On November 4th, 2003, The sun produced a flare so powerful it saturated the X-ray detectors on the satellites built to measure it. The instruments maxed out. They were designed assuming nothing would exceed a certain brightness, and the flare blew past it, so the recorded value had to be reconstructed afterward from indirect data. It's been estimated as high as X28, and by some reconstructions even higher, which would make it the most powerful flare measured in the era of modern instruments. The sensor couldn't hold the number. The sun overflowed the cup we built to catch it, 2 years after the peak. On the slope everyone thought was the safe part of the ride. And these weren't harmless light shows. The Halloween storms left a trail. In orbit, satellites took a beating. Operators put dozens of spacecraft into protective safe mode to ride it out. Instruments were damaged. One science satellite, a joint Japanese mission called Midori 2, stopped working entirely around the peak of the storming, its useful life cut short. Astronauts aboard the International Space Station had to move into the more shielded parts of the station to limit their radiation dose. The radiation was strong enough that it wasn't just an equipment problem, it was a human safety problem, in orbit, in real time. Down on the ground, the effects rolled across the planet. Aviation routes over the poles, where the protective magnetic shielding is thinnest, were rerouted to lower latitudes to keep crews and passengers out of the elevated radiation and to keep their high-frequency radio working. Each reroute costs fuel, time, money, but the alternative was flying blind and irradiated, so the planes went the long way around. GPS positioning degraded. High-frequency radio blacked out across the sunlit side of the Earth, again and again, as flare after flare hit. And in Sweden, the storm reached down and did the thing we worry about most. It knocked out power. About 50,000 people in the city of Malmö lost electricity for roughly an hour when the geomagnetic storm overwhelmed part of the grid. A modest outage, in the scheme of things. An hour, one city. But it was a live demonstration, in 2003, of a current from the sky pushing into the wires on the ground and tripping a power system offline. The aurora, for the few who could see them through the season, blazed down to latitudes that almost never get them. The lights were reported far from the poles, deep into mid-latitudes, a sky-wide signature of just how hard the planet was being hit. Now hold the whole picture in your head. This was not solar maximum, this was 2 years after. This was the part of the cycle that, by the logic we walked through earlier, should have been winding down, and it produced a flare that broke the instruments, irradiated astronauts, rerouted air traffic across the globe, and dropped a European city into the dark. The declining phase did that, the supposedly safe slope. If 2003 were the only example, you might call it a fluke, a statistical freak, the kind of thing that happens once and never repeats. But it isn't the only example. The very next cycle did the same thing. It waited until everyone had relaxed, and then it fired its hardest punches years after its peak. And that one I can date even more precisely, because the biggest flares of that whole cycle came in a single month that, on paper, had no business being the most violent stretch of the entire 11 years. That month was September of 2017, and we were, once again, years past the maximum. Solar Cycle 24, the one before the cycle we're in now, was a weakling. It peaked around 2014, and even at its peak it was one of the quietest maxima in a century. Low spot counts, modest activity, the kind of cycle that lulls you. If any cycle was going to let the world forget about space weather, it was this one. Weak peak, weaker afterward, nothing to see here. Then came September 2017, 3 years after that feeble maximum. In the first half of that month, a single active region, catalogued as AR4673, transformed. It came around looking fairly ordinary, and then, over just a few days, it grew and complexified at a startling rate, its magnetic field tangling into exactly the kind of sheared, multipolar knot we talked about, and then it unloaded. On September 6, 2017, it fired an X9.3 flare, the most powerful flare of the entire solar cycle, bigger than anything the cycle managed at its own peak 3 years earlier. And it wasn't alone. The same region produced an X8.2 on September 10th, along with a barrage of other major flares packed into that one stretch of days. Sit with that. The two largest flares of an 11-year cycle did not happen at the cycle's maximum. They happened 3 years into the decline, off a cycle that was supposed to be too weak to matter, from a region that assembled itself almost out of nowhere. And they did damage on the ground in a way that's almost cruel in its timing. September 2017 was hurricane season in the Atlantic. Hurricane Irma was tearing through the Caribbean. Hurricane Jose was right behind it. And right at the moment when emergency responders, ships, aircraft, and storm-battered islands needed their radios most, the X-class flares blacked out high-frequency radio across the sunlit side of the Earth. There were documented periods, lasting around an hour at a stretch, where HF communications used for disaster response and aviation simply went dead, swallowed by the flare's radiation thickening the upper atmosphere. The sun picked the worst possible week to remind everyone it was still loaded. 2 cycles in a row, 2 clean demonstrations. Cycle 23 fired its instrument-breaking monster 2 years after peak, in 2003. Cycle 24 fired its 2 biggest flares 3 years after peak, in 2017. Different cycles, different strengths, same pattern. The headline danger fades. The real danger doesn't follow the headline. So let's come back to today and do the simple arithmetic, because it's the whole reason this matters to you right now. Solar Cycle 25 was declared at maximum in October of 2024. As I'm recording this, we are roughly 20 months past that. 20 months. The Halloween monster came at about 24 months. The September 2017 flares came at about 36 months. We are walking into the exact window, the same stretch of the cycle, measured from the peak, that produced the 2 worst flare events of the previous 2 cycles. We're not approaching it, we're in it. And I want to be precise, because precision is the point. This does not mean a record flare is scheduled. The sun does not run on a timetable, and anyone who hands you a date is selling something. What it means is that the part of the cycle we have now entered is, historically, the part that bites. The probability of a major event is not winding gently down towards zero the way the comfortable story implies. It's sitting in the zone that has, twice in living memory, produced the biggest shots of the whole cycle. So when NOAA breaks routine to flag a large, complex region rotating into view, in this phase, in this window, the forecasters aren't being dramatic. They're being students of their own history. They've seen the declining phase do this. They know better than to call it safe. Now, everything we've talked about so far has been radiation and radio and satellites, things up there, things in orbit, things in the sky, and it's easy to keep it at arm's length, to think of space weather as a problem for astronauts and pilots and satellite operators, not for you, in your house, with your refrigerator running and your lights on. So let me close that distance. Let me take you to the one night that proved a storm on the sun can reach all the way down through 93 million miles of space, into the ground beneath a major modern city, and switch off the power to millions of people before they'd even finish sleeping. It took 90 seconds. March of 1989. The sun was, you guessed it, on the declining side of its cycle. Early that month, a large active region rotated across the disk and began firing. On March 6th, it produced an enormous flare, an X-15, one of the strongest of that era. And over the days that followed, March 10th through 12th, it hurled coronal mass ejections out into space, billion-ton clouds of magnetized plasma. And the geometry that month was bad. The clouds were aimed at us. They crossed the gap in a couple of days, and late on March 12th and into the early hours of March 13th they arrived. When a CME hits Earth, it slams into the planet's magnetic field, and, if its own magnetic orientation is just wrong enough, it pours energy into that field and sets the whole thing ringing. The magnetic field around the Earth starts to shake, and here's the piece of physics that turns a pretty sky into a catastrophe. A changing magnetic field induces electric currents in any long conductor sitting inside it. That's not exotic. That's the same principle that runs every electric generator on Earth. Move a magnetic field near a wire, and you drive a current through the wire. Now look at what we've draped across the surface of our planet. Power lines. Thousands of miles of high-voltage transmission line, strung continent to continent. pipelines, railways. To a geomagnetic storm, the power grid is just an enormous antenna laid out across the ground, waiting to catch a current it was never designed to carry. We call those geomagnetically induced currents. Direct current, shoving its way into a system built to run on carefully balanced alternating current. On the night of March 12th into 13th, 1989, the sky over Canada lit up. The aurora pushed so far south that people reported it deep into the United States, as far as Texas and Florida. A glowing red sky that some who saw it thought was the reflection of a distant fire or something worse. It was beautiful, and it was the visible edge of a current that was, at that very moment, forcing its way into the power grid of the province of Quebec. Quebec was uniquely exposed, for a reason that is going to matter enormously when we come back to the United States in a few minutes. The province sits on top of the Canadian Shield, a vast slab of ancient, hard, electrically resistant rock. When the ground itself doesn't conduct electricity well, the induced currents take the easier path. They climb into the power lines instead. Quebec's grid also relied on very long transmission lines, running roughly north to south, carrying power down from massive hydroelectric stations in the far north to the cities in the south. Long lines, over poorly conducting rock, are the perfect setup, the worst-case geometry for catching a current from the sky. At 2:44 in the morning, the storm found the weak point. The induced currents had been pushing into the system, destabilizing the equipment that keeps the grid balanced. Devices that regulate the flow began to trip offline, one after another, in a cascade. And once the first few went, the rest followed in a chain reaction far faster than any human operator could react to. The entire Hydro-Quebec grid collapsed. 90 seconds. From the first major trip to total blackout, the whole thing came down in about a minute and a half. There was no time to do anything. No warning on the floor, no chance to shed load gracefully, no opportunity for a person to step in and stop it. By the time the operators understood what was happening, it had already happened. 6 million people lost power in March, in Quebec, where the overnight temperature was around 15 below 0 Celsius. Roughly 6 million people went dark and cold at 2:45 in the morning, most of them asleep, most of them with no idea that the cause was a cloud of plasma launched off the sun 3 days earlier. The blackout lasted around 9 hours. Schools and businesses closed. The Montreal metro was disrupted. The regional economy took a direct hit. People woke up into a dead grid and a freezing house and reached for light switches that did nothing. And the damage didn't stop at the border or at the lights. That same storm drove currents into systems far to the south. In the United States, at a nuclear plant in New Jersey, a large transformer was damaged badly enough that it had to be replaced. These are not parts you keep in a closet. A large high-voltage transformer can be the size of a house, can take many months to a year or more to build, often custom-ordered. The storm reached into the American grid and destroyed hardware that takes a year to replace. And the only reason it wasn't worse is that the geometry favored Quebec that night, not New York. Let me say the number one more time, because it's the number that should stay with you. 90 seconds. That's how long the modern world, in one well-developed province, took to go from normal to total grid failure once the current from the sky found its way in. Not a slow decline, not a rolling series of warnings. 90 seconds, in the dark, at 2:44 in the morning. 1989 was the warning shot. It was, in the grand scale of solar storms, not even the big one. It wasn't close to the worst the sun can do. To see the ceiling, the real ceiling, you have to go back further, to a storm so large that when it hit, the technology of the day literally caught fire. And the people who study these things will tell you, quietly, that it's only a matter of time before something like it comes again. To understand the ceiling, go back to the first day of September, 1859. A British astronomer named Richard Carrington was at his telescope, doing what he did most days, sketching the sunspots projected onto a screen. The sun was busy that season, covered in a sprawling, complicated group of spots. And while Carrington watched, something happened that no one had ever recorded before. 2 brilliant points of white light flared up within the sunspot group, bright enough to be seen in ordinary white light, blindingly so. They blazed for a few minutes and faded. Carrington had just become the first human being to witness a solar flare, and not just any flare. He'd seen the muzzle flash of the largest geomagnetic storm in recorded history. What he couldn't see was the coronal mass ejection that came with it, an enormous cloud of plasma launched off the sun and aimed, that time, almost perfectly at Earth, and it came fast. Most CMEs take a day or more to cross the gap. This one made the trip in around 17 hours, which tells you how violently it was thrown and also suggests it had help, that an earlier eruption had cleared the path ahead of it, so the main cloud could come barreling through with less to slow it down. It arrived on September 1st and 2nd, and when it hit, the planet lit up. Aurora was seen at latitudes that simply never see them, down into the Caribbean, over Hawaii, in Colombia, close to the equator. The lights were so bright in some places that people got out of bed thinking it was dawn. Gold miners in the Rocky Mountains reportedly started cooking breakfast at 1 in the morning, fooled by a sky that glowed like daytime. Newspapers described skies the color of blood and flame from one hemisphere to the other. And then the technology of the age began to fail, in a way that had never happened before because the technology itself was barely 20 years old. The telegraph, the world's first electrical network, the first time humanity had strung long conducting wires across the landscape on a large scale. Exactly the kind of long conductor a geomagnetic storm loves. Telegraph systems across Europe and North America went haywire. Operators got electric shocks from their equipment. Sparks leapt from the lines and from the instruments. Telegraph paper caught fire in some offices. And then came the detail that sounds like fiction but is in the historical record. Some operators discovered they could disconnect their batteries entirely, the power source the system needed to run, and keep sending messages anyway, the lines carrying current supplied purely by the storm in the sky. The aurora was running the telegraph. For a while, the Earth's own electrified atmosphere was powering the network, and then it was frying it. In 1859, that was a fascinating catastrophe, and a manageable one. The telegraph was new. Most of life didn't depend on it. You could lose every telegraph line on the planet, and the vast majority of people would simply go on with their day, because their world ran on muscle and fire and daylight, not electricity. The Carrington event hit a civilization that was barely plugged in. Now ask the obvious question. What happens when a Carrington-class storm hits a civilization that is nothing but plugged in? Because that's us. Everything you depend on traces back to the grid. Water arrives at your home because electric pumps push it there. Food reaches your store because refrigeration and transport and payment systems all run on power. Your money is numbers in a networked computer. Fuel comes out of a pump because electricity drives it. Hospitals, traffic lights, the cell tower that carries your voice, the data center holding your entire digital life. Every bit of it sits downstream of the same electrical grid that, in 1989, a far smaller storm brought down in 90 seconds. The Carrington event is estimated to have been somewhere around twice as strong as the 1989 Quebec storm, possibly more. It is the benchmark. It is the number the people who plan for these things keep taped to the wall. And the unsettling consensus among the scientists who study it is not that a storm like this might happen someday in the abstract. It's that storms of this class have hit the Earth before and will hit it again, and the only open questions are when, and whether we'll be aimed at it when it comes. We even got a near miss in recent memory. In July of 2012, a Carrington-scale CME erupted off the Sun and tore through Earth's orbit. It was measured by a spacecraft that happened to be in its path. The only reason it didn't hit us is timing. It crossed the place where Earth would be, but Earth wasn't there yet. We had moved on in our orbit. The bullet passed through the spot we'd occupied about a week earlier. Miss it by a week, and you'd very likely have been reading about the great storm of 2012 for the rest of your life. So the ceiling is real, it's documented, and we've been grazed by it within the last decade and a half. The question that should be forming in your mind by now is the practical one, the American one. If a storm like that pushed its currents into the grid we actually live on today, what would it find? How exposed are we, really? The answer has a lot to do with the rock under your feet, and for a huge swath of the United States, that rock is exactly the wrong kind. Remember why Quebec went down so fast in 1989? It wasn't just bad luck, it was geology. The province sits on the Canadian Shield, ancient hard rock that conducts electricity poorly, so the storm's induced currents climbed into the long power lines instead of dissipating into the ground. Bad rock, long lines, fast collapse. Here's the part that should get an American audience's attention. That same kind of rock doesn't stop at the border. The geological structures that make a region vulnerable to these currents extend down into the United States, and the US Geological Survey has spent years mapping exactly where. According to the USGS, a solar superstorm would adversely affect telecommunications and electric power transmission systems across the United States, and they single out two regions as especially exposed: the Midwest and the East Coast. The most populated, most economically dense corridor in the country sits over ground that, electrically speaking, helps the storm rather than absorbing it. It comes down to a property called ground conductivity. Where the rock beneath the surface conducts electricity well, induced currents have somewhere to go, they sink into the earth and dissipate. But where the rock is old and resistant, like the formations under parts of the Midwest and the Northeast, the currents don't sink. They look for the next best conductor, and the next best conductor is the power line strung overhead, the buried pipeline, the railway. The grid becomes the path of least resistance for a current born 93 million miles away, and then layer the grid itself on top of the geology. The American high-voltage transmission network is enormous, and it's old. Long lines running across exactly the wrong rock, and at the heart of it, the single most vulnerable and most irreplaceable component, the large power transformer. I want to spend a moment here, because the transformer is the quiet villain of this whole story, and almost nobody thinks about it. A large high-voltage transformer is a massive thing, often the size of a small house, weighing hundreds of tons. It steps voltage up and down so power can travel long distances and then be made safe for your home. The grid cannot function without them. And here's the problem. They are not designed to handle direct current pushing through them. The geomagnetically induced current from a solar storm is, effectively, direct current. And when it floods into a transformer built for alternating current, it drives the transformer's magnetic core into a state called saturation. The transformer starts to overheat. In a severe enough storm, it can cook itself from the inside, permanently. Now here's why that's the nightmare. These transformers are not stockpiled. Many are custom built for the specific spot they sit in. They're often manufactured overseas. Lead times to build and deliver one can run many months, in some cases more than a year. We keep a limited number of spares. So picture a severe storm that doesn't just trip the grid offline, the way Quebec went down for 9 hours, but physically destroys dozens or hundreds of these transformers at once, across the Midwest and the East Coast simultaneously. You don't restart from that in 9 hours. You don't restart from that in 9 days. If the hardware itself is dead, and the spares are gone, and the factories that build the replacements are themselves running on damaged grids and a year-long backlog, then the lights in the worst-hit regions could stay off not for hours, but for weeks, months, in the grimmest credible scenarios, longer. And everything we listed earlier, the water pumps, the refrigeration, the fuel, the payments, the hospitals, all of it stays down with the grid. This is not a fringe scenario invented to scare you. This is the shape of the risk, as the people who actually plan for it understand it. It's why the USGS maps ground conductivity across the country. It's why NOAA's Space Weather Prediction Center exists and runs around the clock. It's why grid operators have, in recent years, started building procedures to reduce load and protect equipment when a severe storm warning comes in, the kind of deliberate, graceful step-down that nobody had a chance to perform in Quebec in 1989 because it came too fast. The defenses are real, and they're better than they were. That's the honest, non-doom part, and we'll come back to it, because it matters. But the exposure is also real. The rock is what it is. The lines are where they are. The transformers are what they are. And the thing that decides whether all of this stays a tabletop exercise or becomes a lived event is, simply, whether a big enough storm arrives aimed at us. Which brings the whole story back down to Earth and back to the present. Because we are not talking about an abstract future storm anymore. We have already, very recently, felt the lighter version of all this. It happened in May of 2024, and most people remember it only as a beautiful night of color. They don't remember the $500 million it quietly cost, or the people for whom it was not beautiful at all. In May of 2024, for 2 or 3 nights, a huge part of the world looked up at a sky most of them had never seen before. A cluster of powerful CMEs fired off a big, complex active region, slammed into Earth one after another, and drove the strongest geomagnetic storm in about 2 decades. A G5, the top of the geomagnetic scale. NASA later described the auroras it produced as possibly among the strongest displays in the past 500 years. The lights pushed down into the southern United States, into places like Alabama and Florida, latitudes where people have no cultural memory of aurora at all, because it essentially never happens there. Phones came out by the millions. The whole event became, online, a kind of global celebration, a free light show, a good night. And it was. For most people, that's all it was, and there's nothing wrong with the wonder. But I want to show you the other face of that same storm, the part that didn't trend, because it's the part that tells you what these events actually cost when they touch the ground. It was planting season across the American Midwest, and modern American agriculture runs, to a degree most people never realize, on GPS. Not GPS for directions, GPS for precision. The big tractors and planters that work those enormous fields steer themselves using satellite positioning accurate down to the inch, driving dead straight rows, placing seed and fertilizer with a precision no human hand can match across thousands of acres. The whole system depends on a clean, accurate satellite signal and a geomagnetic storm-wreck satellite positioning. The same disturbance in the upper atmosphere that blacks out radio also smears and degrades the GPS signal, throwing off the precision that those automated systems need. So during the May 2024 storm, right in the heart of planting season, that precision guidance failed across the Midwest. The self-steering systems lost their accuracy or shut down, and a lot of farmers, on some of the most important days of their entire year, simply had to stop. You cannot plant a crooked, guessed-at field with a machine built to plant a perfect one, not without risking the whole season's yield. The estimated cost of that, just the agricultural disruption from those few days, has been put at around $500 million, $500 million, from a storm that most of the planet remembers as a pretty night. That's the lesson, and it's a precise one. The same storm, at the same moment, was a wonder to a teenager with a phone in Florida and a financial disaster to a farmer in Iowa. Space weather doesn't feel like a catastrophe while it's happening. There's no roar, no shaking, no wall of water. There's a gorgeous sky, and somewhere out of frame, systems quietly failing and meters quietly running. And it wasn't only the farms. The same broad period of intense solar activity in this cycle has been hard on satellites in low orbit, and there's one example that captures the vulnerability perfectly. Back in February of 2022, a fairly minor geomagnetic storm, nothing remotely like a G5, hit just after a batch of 38 Starlink satellites had been launched into a low parking orbit. The storm did something subtle. It heated and puffed up the very top of the atmosphere, and that swollen atmosphere reached a little higher than usual, into where those fresh satellites were sitting. The extra air meant extra drag, and that drag was enough to pull 38 brand new satellites back down into the atmosphere, where they burned up, gone, from a storm that barely registered on the scale. 38 satellites, from a minor event. Now put that next to the $500 million planting season, from a major one, and then remember the 9-hour Quebec blackout, from a storm in between. Stack them up, and you can see the staircase. Minor storms nibble at satellites. Major storms cost industries hundreds of millions and light up half a continent. And the truly severe ones, the Quebec class and beyond, reach all the way into the grid. We are climbing that staircase in real time, in a cycle that has already, in May of 2024, delivered its strongest storm in 20 years. And we are doing it in the declining phase, the phase that, as you now know, has a history of saving its biggest shots for last. So now, finally, we can ask the question this whole video has been building toward, with our eyes open and the receipts behind us. The region rotating into view this week, AR4478, the one NOAA broke routine to warn about. If it does what a region like it is capable of, if it fires a CME while it's pointed at us, what actually happens? Let's walk through it honestly. No hype, just the range of what's real. Let's be disciplined about this. I'm going to give you the realistic range, from the mild end to the severe end, and I'm going to tell you which parts are likely and which parts are worst case, because the difference is exactly what the panic channels erase. Start with where AR4478 actually is right now, today, as I record this. It's still rounding into view, not yet facing us, and the immediate forecast is honestly modest. NOAA's outlook through the end of June has the geomagnetic activity staying fairly low, with the KP index, the scale we use for storm strength, peaking only around 4. 4 is below the threshold where we'd even call it a storm. So in the very short term, if the region fires right now, most of what it throws sails wide of Earth because of the geometry. It's still off to the side. That's the honest mild end. This week, probably not much, at least not at the ground level you'd feel. But the region is rotating, and around June 27th, into the first days of July, it swings toward the central part of the sun's face, the part pointed at Earth. That's when the geometry flips from throwing wide to aimed. And that's the window the forecasters are actually watching, not today, but the days when a CME off this region would come straight down the line at us. So picture it fires then, while it's facing us. What's the chain of events? First, the flare. Light and X-rays, arriving 8 minutes after the eruption, the instant we see it. If it's a strong flare, an M-class or an X-class, the sunlit side of Earth gets a radio blackout. High-frequency radio degrades or dies for anywhere from minutes to a couple of hours. For most of us scrolling our phones, that's invisible, because your phone doesn't use HF radio. But for transoceanic flights, for ships, for ham operators, for emergency and aviation communications over the poles and oceans, it's real. Remember September 2017, when flare blackouts hit during a hurricane response. That's the layer that arrives first and fast, and there is no warning for it. Then, if the eruption launched a CME, the clock starts. 15 hours to maybe 3 days of transit, depending on its speed. And during that window, this is the good news, we actually get a warning. Spacecraft parked between us and the sun catch the cloud, measure its speed and, crucially, the orientation of its magnetic field, because that orientation is what determines whether it couples hard into Earth's magnetic field or mostly slides past. Forecasters issue the watch. Grid operators get the heads up they never had in 1989. Then it arrives, and here's the realistic spread of what a moderate to strong CME from a region like this does. On the likely end, you get a nice geomagnetic storm, aurora pushed to lower latitudes. Though remember, it's summer, the nights are short, so fewer people see it than in May of 2024. Some GPS degradation, the kind that nudges precision systems and annoys surveyors and farmers. Minor, manageable satellite drag, possibly some localized grid voltage irregularities that operators ride out using exactly the procedures they've built since Quebec. That's the probable outcome of a solid hit. Disruptive at the edges, costly to a few industries, spectacular in the sky, survived by the grid. The severe end, the genuine worst case, is the one we spent this whole video building toward, and I'm not going to pretend it's the likely outcome from this specific region, because I don't know that, and neither does anyone. The severe end is a fast, powerful, badly oriented CME, or a 1-2 punch of them clearing the path for each other the way the Carrington storm was cleared, hitting the grid over that vulnerable Midwest and East Coast rock, hard enough to drive the induced currents past what the system can ride out. Transformers saturating. A cascade. The Quebec scenario, but potentially wider, because the storm is bigger and the geometry is worse. That's the tail. Low odds on any given storm, not zero, and the consequence is so large that the people who plan for the grid take the low odds tail very seriously, because you don't get to be unprepared for it twice. So that's the real range, from a pretty sky to a continental problem, and AR4478 is the specific region that has earned a place on the watch list as it turns to face us over the next week and a half. Now, if you've made it this far, you have a clearer, more accurate picture of this than almost anyone shouting about it online. Which means it's time to deal with the shouting, because the moment NOAA flagged this region, a second sun rose, made entirely of nonsense. Kill shots, micronovas, flares triggering earthquakes, pole shifts. A whole industry that takes a real, fascinating, genuinely serious phenomenon and drowns it in fiction, usually to sell you something. So let's separate the signal from the noise, one claim at a time, and show you why, in this case, the truth is actually more unsettling than the conspiracy. So let's take the big claims one at a time and put each one against the physics. Not to mock anyone, but because the real thing is unsettling enough that it deserves to be seen clearly, without the fog. Claim 1. The micronova. The solar killshot. The idea, pushed hard in certain corners of the internet, that the sun is about to detonate, to blast off a layer of itself in a single civilization-ending superflare on a schedule, soon. Here's the problem. There is no physics for it. A micronova of the kind these channels describe is not a recognized phenomenon for a star like ours. Our sun is a stable, middle-aged, main-sequence star. The energy source for a true nova is a completely different beast, a dense stellar remnant, pulling material off a companion star until it ignites a runaway explosion on its surface. The sun has no companion feeding it. It has no mechanism to do that. The machinery the claim requires simply isn't there. When you ask the people making the claim to show the energy source, the actual physical process, you get vibes and edited diagrams, not a mechanism. And a catastrophe with no mechanism is a story, not a forecast. Now, I'm going to do the thing the killshot channels never do, which is tell you where the real edge of the science actually is, because it's more interesting than the fiction. There is a genuine open question in solar physics about superflares. Astronomers using planet-hunting telescopes like Kepler and TESS have watched thousands of distant sun-like stars, and some of them do produce flares far larger than anything we've recorded from our own sun. That's real, it's peer-reviewed, and it's actively studied. The honest question scientists are wrestling with is whether our sun is capable of a rare superflare, and if so, how rare. But, and this is the whole point, that operates on timescales of centuries to many thousands of years, and even the biggest of those is nowhere near the planet-cracking micronova of the conspiracy version. The real science says, maybe, very rarely, somewhat bigger than Carrington. The fiction says, definitely, soon, apocalyptic. Those are not the same claim, and the gap between them is where the grift lives. Claim 2. Solar flares cause earthquakes. Every time a big region appears, this one resurfaces. Flare on the sun, quake on the earth, surely they're connected. They're not, and the reason is energy and mechanism. The energy a flare actually deposits into the solid body of the Earth is minuscule compared to the colossal stresses already stored in tectonic faults, stresses built up over years to centuries by the grinding of plates that weigh quadrillions of tons. A fault ruptures when its own accumulated stress crosses a threshold, and that threshold dwarfs anything a burst of solar radiation or a geomagnetic current does to the crust by many orders of magnitude. People have looked, repeatedly, for a statistical link between solar activity and global earthquake rates, and the robust result is that there isn't a meaningful one. Earthquakes happen during solar maximum, during solar minimum, during flares, during quiet, at the same tectonic pace they always have. The sun does not load the San Andreas. Plate tectonics does. Claim 3. The pole shift. The idea that a storm is about to flip the Earth over, or flip its magnetic field overnight, with cataclysmic results. This one launders a real thing into a fake one. The real thing, the Earth's magnetic North Pole genuinely does wander, and it has been drifting at a noticeable pace in recent decades, enough that the global navigation models have to be updated to keep up. That's documented, it's tracked, it's in the World Magnetic Model. The real thing also includes the fact that, over enormously long geological timescales, hundreds of thousands of years between events, the Earth's magnetic field has fully reversed, north becoming south, many times in the deep past, recorded in the rock. But the fiction welds those two true facts into a false one, that a solar storm will trigger a sudden overnight flip with the ground heaving and the poles physically tumbling. There's no mechanism for a CME to do that. The slow drift is real, and harmless to you. The ancient reversals are real and take millennia. A storm-triggered instant flip is neither. So strip all three away, the micronova, the flare quakes, the pole flip, and you might think we're left with reassurance. We're not. And this is the part I most want you to hold on to, because it's the spine of how this channel sees the world. The truth that's left over, once you clear out the fiction, is more unsettling than the conspiracy, not less. Because the conspiracy versions all share one strange comfort. They imply a plan, a schedule, someone or something in control, a date on the calendar, a hidden order to it all. And the real picture has none of that. The real picture is a violent, indifferent star that fires when its own tangled magnetism decides to fire, on no schedule we can read, aimed wherever the geometry happens to point, at a planet that has wired itself more deeply and more fragilely with every passing year. There's no countdown. There's no controller. There's just physics and exposure and timing. And that, the absence of anyone at the wheel, is far scarier than any kill shot. We'll come back to that thought at the very end. First, let's talk about what the grown-ups, the actual scientists, are genuinely uncertain about and what they're doing about it. Clearing out the fiction doesn't mean the science is all settled and tidy. There are real open questions here, real debates among serious people, and they're worth more of your attention than any kill shot video, because this is where the actual frontier is. The first honest uncertainty is the one we touched on. How big can our sun get? We have good records of solar storms going back to the space age, decent ones back to the telegraph era, and clever proxies, like spikes of certain isotopes in tree rings and ice cores, that let us hunt for giant storms in the more distant past. And those proxies have turned up evidence of events, centuries ago, that may have been substantially larger than Carrington. The debate is over how large, how often, and whether our specific star can produce the kind of superflare we see on some other sun-like stars. There's no consensus on the ceiling. Scientists genuinely argue about it. That's not a weakness in the science. That's the science working, and it's a long way from the sun explodes next Tuesday. The second honest uncertainty is prediction itself. We are good at some parts and bad at others. Once a CME launches, we can track it and forecast its arrival reasonably well, within a window of hours. That part has improved enormously. But predicting whether a given region will erupt at all, and exactly when, and how strong, that we cannot do reliably. We can say a region is complex and capable, the way NOAA said it about AR4478. We can put a probability on it, 50-50 for a blackout. But we cannot tell you that it will fire at 3 o'clock on Tuesday, and anyone who does is making it up. The sun keeps its timing to itself. So what do the serious people do with that uncertainty? They prepare, in ways that don't make headlines. NOAA's Space Weather Prediction Center runs around the clock, every day of the year, feeding forecasts to the people who need them: the power companies, the airlines, the satellite operators, the military. Grid operators have, especially since the wake-up calls of recent decades, built real procedures for when a severe storm warning comes in. They can reduce the load on the system, reconfigure it, take vulnerable equipment offline deliberately, the graceful step-down that Quebec never got the chance to perform. Some utilities have installed devices to block those induced currents from reaching the most vulnerable transformers. There's serious, ongoing work on building a reserve of spare large transformers, so a continent-wide hit doesn't mean a year-long wait per unit. Is it enough? Honestly, probably not for the true worst case. The Carrington-class tail event would still hurt, badly, and the experts who study it will tell you that candidly. But the gap between 1989 and now is real, and it matters. In 1989, the storm hit a grid that didn't see it coming and had no playbook. Today, a storm arrives at a system that is watching for it, that has a warning window, that has rehearsed the step down. That's the difference between a disaster and a managed crisis, at least for everything short of the absolute ceiling. And there's a role in this for you, a modest and unglamorous one, which is the only kind I'll ever sell you on this channel. Not a bunker, not freeze-dried buckets and gold coins. Just the same basic resilience that serves you for any blackout, a hurricane, an ice storm, a solar event. It doesn't care about the cause. A few days of water, some food that doesn't need power, a way to keep a phone charged, a radio that runs on batteries. Cash, because card readers and ATMs are grid-dependent. The single most exposed point in the whole system, the long-duration transformer-level blackout, is also the one where ordinary preparedness, the kind emergency managers have begged people to do for decades, actually buys you time and calm. That's it. That's the ask. Be the household that has water and a flashlight, not the one fighting over the last case of bottled water on day 2. That's the responsible picture. A real, serious, low probability, high consequence risk, watched by competent people, partially defended, with a sensible role for you that doesn't require fear, which is the exact opposite of what the killshot channels offer, which is enormous fear and a checkout link. So let's bring it home, back to the actual region, the actual sun, the actual next 9 days. Because while we've been walking through history and physics, AR4478 has been doing what every feature on the sun does. It's been turning, and it's almost in position. So here's where we actually stand as this video goes out. AR4478 has rounded the eastern edge of the sun and is marching across the disk, the way every active region does, carried by the sun's roughly 27-day rotation. Right now it's still off-center, which is why the near-term forecast is calm. The geometry still throws most of what it produces wide of Earth. But over the coming days, through about June 27th and into the first days of July, it rotates toward the central meridian, the center line, the position that points straight at us. That's the window, not because anything is scheduled, the sun doesn't schedule, but because that's when the geometry is loaded. If this region is going to matter to Earth, the days when it's facing us are the days it matters. A flare while it's centered means the radio blackout hits our daylit side square on. A CME while it's centered means the cloud comes down the line toward us instead of off into empty space. Forecasters will be watching its magnetic complexity hour by hour, looking for whether it's growing more tangled or relaxing, because that's the tell for whether it's winding up or winding down. They'll be watching the flare output. And the moment anything erupts earthward, that warning window opens, the hours to days of transit time that are the only heads up the planet ever gets. This is the part I can't write in advance, and I want to be straight with you about that, because the honesty is the whole brand. By the time you're watching this, the region may have fired something significant, or it may have rotated across, quiet the whole way, and sailed off the western edge having done nothing but throw a few sea flares from behind the limb. Both are completely possible. That uncertainty is not me dodging. That uncertainty is the actual state of the science. We can tell you the gun is loaded and turning toward us. We cannot tell you if or when the trigger gets pulled. But now go back to the question I planted at the very start, the one I promised we'd come back to. I told you the reason NOAA was worried wasn't the thing you'd think, and here's the payoff. The worry was never really about this one sunspot. AR4478 might amount to nothing. The worry, the real one, the one this whole story has been about, is the gap. The gap between how dangerous the sun actually is in this exact phase of its cycle, and how safe everyone has decided it is. AR4478 is just the messenger. It's the region that happened to rotate into view and remind the forecasters, and now you, that the declining phase is the phase that bites, that the biggest storms in living memory came years after the peak, and that we are sitting squarely in that window right now, with the public's attention at low tide. That's why a single special bulletin for one sunspot is worth a whole video. Not because this spot is the apocalypse, because this spot is the proof that the calm is a story we told ourselves, and the sun never agreed to it. So what should you actually do with all this? Almost nothing, and that's the honest answer. You don't need to panic about AR4478 specifically. You don't need to refresh the solar dashboards at 2 in the morning. That's my job, and I'll do it for you. What you need is to delete the false belief that this threat ended in October of 2024. It didn't. It changed shape. It got quieter on the surface and kept its teeth. Carry that one corrected idea and the basic preparedness that's smart for any blackout, and you're ahead of almost everyone. Because the people who get hurt by these things, historically, are never the ones who were watching. Quebec didn't get hurt because the storm was unstoppable. Quebec got hurt because it arrived at 2:44 in the morning at a system that wasn't braced. The farmers in 2024 didn't lose $500 million because the storm was secret. They lost it because nobody told them. A beautiful aurora and a planting disaster are the same event wearing two faces. Being unsurprised is most of the battle, and now you're unsurprised. So let me leave you with the thought I promised at the start, the one that's been sitting under this whole story, because it's the truest and the most unsettling thing I know about the sun. Here's the one line to carry out of all of this. The sun didn't get safer in October of 2024. It got quieter on the surface, and it kept every bit of its power. The danger didn't end. It went undercover. And the reason that should stay with you isn't fear. It's the strange clarity underneath it. Every conspiracy version of this story, every kill shot, every secret schedule, every hidden hand steering disasters at us, they all share one buried comfort that nobody admits to. They imply that someone is in control. That there's a plan, a date, a controller, a reason. Even the darkest version, the one where shadowy forces aim catastrophes at us, is secretly reassuring, because a world with a villain at the wheel is a world that at least has a wheel. Somebody's driving. It means something. The real picture is the one without a driver. The real picture is a star, 4.5 billion years old, burning through the middle of its life, churning its own magnetism into knots because that's just what a rotating ball of plasma does. And every so often one of those knots snaps and a piece of the sun comes off and it flies out into the dark in whatever direction the geometry happened to point. Not aimed at us, not aimed at anyone, just thrown. And whether it hits us comes down to where Earth happens to be in its orbit on the day the knot decided to let go. In 2012, a Carrington-class storm tore through our orbit and missed us by about a week, purely because we hadn't arrived yet. No one spared us. We were just somewhere else. That's the unsettling truth the conspiracies are running from, not a hidden order. The absence of one, a magnificent, indifferent machine, and a planet that has spent 2 centuries wiring itself more tightly and more fragilely into a single electrical web, standing in a cosmic shooting gallery where the shooter isn't aiming at all. No malice, no mercy, no schedule, just physics and exposure and timing and a roughly 27-day rotation slowly bringing the next loaded region around to face us, over and over, for as long as the sun shall live. The truth is more unsettling than the conspiracy, because no one is in control, and no one ever was. But here's the other side of that same coin, and it's where I'll actually leave you, because indifference cuts both ways. A universe with no villain is also a universe with no curse. The sun isn't out to get us. There's nothing personal in it, nothing fated, nothing we did to deserve it, which means the whole game is just understanding and preparation. Watch the star, know the phase, keep the warning systems running, brace the grid, keep some water and a flashlight. That's not the posture of a victim waiting for a kill shot. That's the posture of a species that grew up enough to look its indifferent star in the eye and say, "Fine, we'll watch you ourselves." So that's what we'll do here. We'll watch it for you. When AR4478 reaches center, when it fires, or doesn't, when the next complex region rounds the limb, we'll be on it, with the real data and the receipts, and none of the nonsense. And there's a piece of this story we haven't touched yet that I think changes how you'll see everything we just covered. Because all of this, the flares, the CMEs, the grid, every bit of it, depends on one thin, invisible thing standing between you and the full force of the sun. A magnetic shield wrapped around the whole planet that you never think about and could not live for an hour without. It's the only reason a CME means a pretty sky and a grid scare instead of the end of life on the surface. And right now, in one specific spot over the South Atlantic, that shield has a weak point that is growing. Satellites have to power down when they fly through it. It's called the South Atlantic Anomaly, and what's happening to it is the next thing you need to understand. That's where we're going next. I'll see you there.